Okay, so I'm an undergraduate student, and once it was taught to me that sometimes we need to start to do things by our own. And if you just as me are interested in signal processing, if you're persuading the subject, if you're studying the subject, so we can share this. So, um, if you are familiar with the book Signals in Linear Systems from Lath, probably you already had passed through this chapter, this part right here, miscellany, and I wanted to cover this topic, and let's jump to power series, and then we can, well, we can cover this. Um, we do not necessarily need to cover in the order that is being give. So let's start from power series. And for that, I will use the book, a course, a calculus course, the volume 4, and is from the author Hamilton Lewis Guiderizi. So this book cover power series on the chapter 8. And okay, so let's use this book to cover the the chapter miscellany from signal in linear systems. So let's an with n greater or equals 0 be a given sequence and let's x0 be a given real so the series is a infinite sum which starts from 0, a infinite sum of an times x minus x0 to the n. So it's called a power series with an coefficients around x0 if x0 is equal 0. So we have the power series around 0 as following: a infinite sum that starts from 0 of an x to the n, which is equal the coefficients. So a0 plus a1x plus a2x squared, and so on. And right here you have to notice that we are just substituting this lower limit on this first coefficient, and it goes to this upper limit, so it goes to infinite. So this is a signal, a sequence, sum of a sequence. And this is a series. And this is a sum of a series. Sum of a sum of a series. And this is the same as a signal. Okay, so if this lower limit starts in 0, so this is, so a0 is equal 0 to the 0, which is equal 1. And let's say now, for this is for n equals 0. So for n equals 0, we have a0, which is again 0 to the 0, which is equal 1. So this is 1. For n equal 1, a1 is equal, sorry, a0 x to the 0, which is equal 1. So a1 n, for n equal 1, So n index the number 1. Instead of we write n, we write the number of the sequence, which is 1, nx 1. So a1 x right here is 0, not 1. Okay. And for n equal 2, this is n2 x2. So again, instead of write the n, we write the number of the index. We write the index as the number of the sequence, and on this case is equal to, and so on. Okay. In this literature extends this for factorial numbers, so it says for example that for a power series so an infinite sum that starts from 0, infinite sum of anx to the n converges. Sorry, I'm skipping the part. I was saying that for this power series around 0, the coefficients, they extend for factorial numbers as well. So for example, this power series, an infinite sum of x to the n over n factorial with the upper limit as infinite and the lower limit as 0. So this power series around 0. So let me write, this is a power series around 0 with coefficient an equal 1 over n factorial. Okay, so these coefficients to this power series extends for these coefficients with factorial numbers. So for example, let's attribute a arbitrary number for n, let's say sequence. Okay, so let's say a sequence 5 a5. So this is the same as 1 over 5 factorial, which is the same as write 1 over 5 times 1 over 4 times 1 over 3 times 1 over 2 and 1 over 1. And this infinite sum will be something like this. So it starts in 0. So let me write the whole power series first. Okay, so 0 plus now x1 and 1. So this is for, okay, so this is for n equals 0. This is for n equal 1. And x2 over 2 plus x3 over 3 plus x4 over 4 plus x to 5 to the 5 over 5 for n equal 2, for n equal 3, for n equal 4, and for n equals 5. And it goes introducing a theorem. And it says that if the infinite sum of a n x to the n converges for x equal x1, with x1 different of 0, then the series it will converges for all x in a open interval. So this is the open interval. x1 module minus module of x1 a module of x1 and goes on demonstrating this theorem. So, demonstration. So this infinite sum of the series an x to the n x1, sorry, converges we have that the limit with n approaching infinite, limit of an x1 to the n approaching with n approaching the infinite is equal 0. And right here, if we substitute this n right here on x, so x will gradually decrease and a point that we will reach 0, but this is only if the module of x is smaller than 1. So this is only if the module of x is less than 1. So x, it will gradually decrease till a point that it will be equal 1, equal 0, sorry. It's something like that. So this is the function. Um, I don't know. Okay, and now the content that it introduced from my perspective, it look like the definition of limit. So it goes saying that then taken, so taken then epsilon equal 1, there's a natural p that for all n greater or equal p, so we got the module of an x1 to the n less or greater than 1. And this is why, from my perspective, it looks like the definition of limit. So if you remember the definition of limit, let's recall the definition of limit and compare to see if there's something with. So the limit definition it says that if we say that the limit of a function of x having x approaching a p number, if for all epsilon greater than 0 there's a delta greater than 0. So this is the limit definition. So 0 less than the module of x minus p is less than delta. So this module in an interval between 0 and a number delta and a function of x, the module of a function of x minus the value of the limit is less than epsilon. And again, if you remember, this is something that we see alongside with the theory of confront. And I'm not so sure right now what I'm doing, what I'm about to do, but maybe I'm wrong, but this is for me is the same as this first part right here. So this is the first element, and this is the element that is on this interaction. Like it can be the element number 1, number 2, for n elements. So for n elements, okay, so this is a way to tie this module, to control this module. So establish that epsilon is equal 1. We are tying the module to 1. We are controlling the module. Okay, and it goes saying that as the module of an x to the n is equal an x1 to the n, this module, times the module of x over x1 to the n. Now let's just rewrite this expression. So we can rewrite this module if we distribute the exponent n, so x to the n, x1 to the n, and we can rewrite this as being the same as xn times x to the n times x1 to the n. And now if we do x and x1 to the n, the module times the module x of x to the n times to the module of x1 to the minus n. Right here is minus n, sorry, because we are now doing the inverse operation. And now we can rewrite this and record the property of exponents. So this is the same as x to the n. Right here is minus n times n. So xn, x1 to the 0, x to the n. So this is 1. So you return the left side of the equation of this expression. Okay. So it results that for all x in all natural n greater or equal p, we have the module of x and x to the n being less or greater than the module of x over x1 to the n. And again, this is because we are imposing this condition, which is, for me, it looks like the limit definition, because if we are saying that epsilon is equal 1, so we are imposing this, and which is a method to controlling the module. And I said that we see limit definition alongside with the Confront theorem. So if you notice right here, we are subtracting the function of the result of the limit. And if we are saying that the module of an x1 to the n is less or equal 1, so let me copy this expression. You can see is this one right here. So let me just change the color again. This is less or greater than 1. Sorry, is less or equal. Less or equal 1. And this is true for all n greater or equal p. So for the module of x less than the module of x1 is the geometric series. Geometric series x over x1, the module of x over x1 to the n converges So let's also just remember how to write the ratio of a geometric progression. So for a geometric progression, we can write the ratio as Q is equal an minus 1, and also the general term as an equal a1 times q to the n minus 1. Okay, now we finish with a example, and the example is it gives us a series. So the series x to the n over n with n starting in 1. So this is the lower limits, and infinite as our upper limit. And something that I don't told to you is that this sum is what characterizes a series. So is a series of a sequence. And we can complement saying that starts in n equals 1, and it goes to infinite. This is the lower limit, and this is the upper limit. Okay, so if we just substitute the lower limit on the sequence, so x to the 1 over 1, so this is equal x. But if you remember, right here we are tying this condition for something like, let's see, it only true if This is only true when x is less than 1. Because the book it doesn't let explicit how he got a converged value of x equal minus 1, but we know that the module of x is equal x if x is greater or equal 0 and is minus x if x is less than 0. So if the module of x is less than 1 tends to 0, for if the module of x is greater than 1, diverges if the module of x is exactly equal 1, so again tends to 0. And now if the module of x is exactly minus 1, so it will oscillate. Okay, and we can represent this right now having x minus 1 as minus 1, having x as minus 1. So the series we can write this way. So the series converges for all x belonging to the open interval between minus 1 and 1. Okay, so this is what was the theory of power series. And again, this part right here is just my impressions, because for me it looks like the definition of limits. So I'm not so sure about this, but I think we were able to do a good analysis of this introduction. And okay, so for now it's all. Hope you like it. If you wanted to leave some comments, feel free. And that's it. Thank you.